Alpha Houston on space to ground 1 for Don. We're ready for your downlink.
Okay, I'm going to hit play.
I'm Don Pettit. I was fortunate enough to be science officer on Expedition 6 to the International Space Station. And during this expedition, we had several kinds of science that we did. We did programmatic science, which is well-planned and well-thought-out science, comes up from the ground and is orchestrated from the ground. And then we have science of opportunity. And this is science that is done at the discretion of the scientists on board space station. And this is kind of the discovery science. And during our mission, we called our science of opportunity Saturday morning science. And this is just showing a little setup on how we make a Saturday morning science video. You can see a little arm bracket coming out from a station rack with one of our cleanest dirty shirts taped up in the background, so we have a nice blue background, and one of these 250 milliliter culture flasks taped to the end of the bogan arm, and it's filled with water and bubbles. And we can watch the motion of these bubbles in this flask during a time-lapse period. So let's go ahead and roll this. Now, here we see time-lapse motion, where every 10 seconds of playtime is about 1 orbital revolution, or a 90-minute period. And look at the motion of these bubbles. These bubbles are seemingly moving rapidly from left to right. If you were to look at this system, you would see no motion. If you just floated by and you looked at it, you'd see no motion. But during time-lapse, you see that these bubbles seem like they move quite vigorously due to the levels of residual acceleration at the microgravity level on space station. So now here's a little cartoon that shows the flask, and this shows a little technical information here. It shows the space station coordinates in X, Y, and Z, along with our attitude, which is this attitude we call XPOP. It's a solar inertial attitude. And then it shows which direction is pointing into the velocity vector. In this case, it's the minus y-axis of space station. And you don't really need to remember all of that stuff, but just look at the resultant bubble motion based on this particular station attitude and the orientation of the experiment in this attitude. And again, about 10 seconds of playtime is one orbital revolution. And look at this bubble motion now in these flasks. They're generally moving in a circle. In a circle. They describe a circle as the station is going around Earth. So that was this inertial attitude XPOP. Now we've changed attitude of space station here, as you can see in this cartoon, and we are in what we call local vertical, local horizontal, which is basically flying around Earth, so the same side of space station points towards Earth at all times. It's kind of flying in airplane mode, as we like to talk about it. And plus X is into the velocity vector. Again, you can see the coordinate system for space station. So let's go ahead and play this video and contrast the bubble motion you see here with what you saw with the inertial attitude. Here, you can see all the big bubbles are already on the right-hand side of the flask. But now, look carefully at the little bubbles. You see they're generally moving to the upper right-hand corner. However, they move up, and now they'll move horizontal, and then sometimes they move down a little bit, and then they move back up again. So the resultant bubble motion you see here is radically different in the LVLH attitude as what you saw in the XPOP attitude. And again, I find this amazing that the attitude of space station, coupled with the orientation of the experiment within space station, can affect the resultant bubble motion or particle velocity for an experiment at the microgravity level. And here we see a third example of this. Again, it's LVLH attitude, local vertical, local horizontal. Again, flying airplane mode around Earth, so that the same side of station points to Earth at all times. And plus Y is in the velocity vector. And you see the coordinate system for space station in terms of the orientation of the flask. So now let's look at the resultant bubble motion. Look at the bubble motion. The big bubbles and the little bubbles are all moving up relative to this flask. So again, we see that even at the microgravity level, where a station is currently operating somewhere between 2 and say 5 micro G, this represents a significant force on fluid and particle systems, and over the course of time can stir things around, as you saw in the time lapse here. And the way they get stirred around depends on space station attitude and the orientation of the experiment within space station for a given attitude. And I found this amazing.
And Houston Alpha, that's it for our Saturday morning science.